Hi everybody. So in a series of two videos, we're going to look at the constrained optimization problem. So this problem has many real-world applications. And in the first video, the first part, we're just going to look at the theory behind the problem and just take a very simple example. In the second part, we'll dive into code. We'll get into Django. We'll get into VS Code Editor and Python as well. So that's going to be the good stuff. But I think before we go into actually coding, it's always really important, I think, to understand a bit about the background of the problem we're trying to solve so you guys have some context. So constraint optimization problem is useful in many different industries and domains. While simple constraint optimization problems are great teaching tools, higher order models solve real world complexities. For example, supply chain and aerospace design. These are just examples, but there are many others. So these advanced systems often involve dimensions beyond 2D visualization, requiring robust computational solvers and algorithms to handle multidimensional variables and strict limitations. So in this part one, and even in the part two as well, we're just going to look at a very simple problem that's representable in two dimensions. But normally, most problems that you're looking at in the real world are not representable on a 2D in two space, like in Cartesian coordinates. It's just impossible. They become too complex, too many variables, too much stuff going on. Real world problems for supply chain, for example, may involve 400 different variables, many different locations, and so it ends up being many dimensions, and that's not you cannot represent many dimensions like that graphically. So the problem we're going to look at today is a furniture factory produces two items, chairs and tables. The factory wants to determine exactly how many of each to build per week to maximize its profits. So operating under limits on available labor and materials. So this is actually like it is a real world problem. There are factories out there that build tables and chairs, but we're simplifying the problem here. Like we're not introducing different different costs that could come about. There may be seasonal constraints as well. Like there may not be a certain the availability of this much material in this season. There may be labor constraints that are seasonal. There could be other costs that are involved. So we're not going to look at that. We're going to simplify it. And the purpose of the simplification is really so we can isolate how the problem works and show it 2D so that you can understand it. So let's assume the factory makes a profit of $45 per chair and $80 per table. X is the number of chairs and Y is the number of tables. So the objective function is the function that defines the goal, in this case to maximize profits. So some optimization problems will be about minimizing and some will be about maximizing. With profits, usually you want to maximize, right? So the goal in this situation is to maximize the profits, and it's always going to be 45x plus 80y in this situation for this particular problem, right? So that's how we're maximizing profits. We want to maximize this particular objective function to see what combination of chairs and tables is going to give us the most profit at the end of the day. So, so let's look at labor hours. So labor hours, building a chair takes 10 hours and a table takes 15 hours. There are a total of 450 carpentry hours available per week. So that's 10x plus 15y is less than or equal to 450. So then material, each chair takes 15 kilograms of wood and each table takes 20 kilograms of wood to make. There are 400 units of wood available per week. So the constrained function there is 5x plus 20y is less than or equal to 400. Non-negativity rules, you cannot make negative numbers of items, and so x must be greater than or equal to 0, and y must be greater than or equal to 0. And so just to define these are what are called inequality constraints. And you can actually have equality constraints as well in these problems, in these optimization problems. But to keep things simple, we'll just deal with the inequality constraints for now. So so the next thing we want to do is rewrite these inequality constraints as y is equal to mx plus b. So the reason we want to do this is that we want to be able to represent these lines, these constraints in two dimensions. to show you guys graphically how this works. And it'll also show us the area where the optimization can actually occur, because the constraints define an area in 2 dimensions where the optimization is actually possible, right? So for labor, we have 10x plus 15y is less than or equal to 450. Rewriting that in the form of y equals mx plus b, just a linear equation. Y is equal to minus 2x over 3 plus 30. So we end up with a y-intercept of 30 and a slope of minus 2 over 3. So for material, same thing. 5x plus 20y less than or equals to 400 was our inequality constraint. And so we rewrite this as y is equal to minus x over 4 plus 20. So y-intercept is 20 and the slope is minus 1 over 4. So showing this on a graph gives us 2 lines. These inequality constraints that we developed, labor and material, and the only area where we can maximize profits because of these constraints, it has to occur in this area right here. So somewhere in this area right here is where we maximize our profit, because it's bounded by these various constraints. And always the optimization, or the value, the highest value is going to occur on one of the vertices of these lines. So it could be at 0, 0 here. It could be at 20, 0, which, you know, 20 on the, sorry, 0, 20 rather. So 0 on the x axis and 20 on the y axis. It could occur right here, or it could occur right here. So it has to occur within this area and on one of the vertices. So that concludes this first video, guys. Just laying out the theory of the problem, the background of the problem. In the second video, I'm actually going to go into some code, and we're going to develop something that we can plug in different values, we can test something, and I'll put everything will be available on, will be up and available on GitHub as soon as possible. So you can download the code and play with it yourself. But that'll conclude this video, and I'll see you guys in part 2.